Hi, so today I'll be presenting the paper Constraint Policy Optimization. I'll basically give you a review of the paper, discussing the background, the motivation of this approach, as well as some of the results, algorithm and its results that's being described in the paper. And at the end, I will also post three questions that was critics that was asked by CEN, one of the classmates in the class, and I'll respond to each question one by one. Um, so let's get started. So before we dive deep into the paper, there's some background knowledge that will be really helpful for you to better understand where the paper was based on. And that was, let me give you a brief introduction to what is reinforced learning. So reinforced learning is a type of machine learning where an agent learns to make decisions by performing actions in an environment that's trying to maximize some notions of the cumulative rewards. So unlike supervised learning, which we may have more experience with, reinforcement learning does not require label input and output pairs and focus on the balance between the exploration and exploitation that tries to maximize its long-term rewards. And as described in the definition, the reinforcement learning have four key components. The first one is the agent, which learns from interacting with the environment. And the environment is the second one, which is where the agent performs the actions. And actions will be chosen by the agents. And at the end, the rewards will be the feedback from the environment to guide the learning process. So now, as we know what reinforcement learning is, let's dive deep into the overview of the constraint policy optimization, which later I'll just abbreviate to CPO. So CPO is a reinforced learning approach that's designed to satisfy safety constraints while trying to optimize its policies. And the purpose of that is to address the need for safe reinforced learning applications and ensures that agents operate within a predefined constraints. Especially for like real world applications, there's different constraints, and we want to have that directly during the learning process. And it is very unique because it's a first general purpose policy search algorithm for constraint reinforced learning with near constraint satisfaction guarantees at each iteration. And the message of that is to integrate the safety constraints directly into the policy optimization process, which allows for later safe exploration. So I'll dive deep into how CPO is achieved and its result later. But before that, let's see where there's some previously related work and backgrounds of the similar approaches. So which is we here have introduced this premium dual methods, so which shares similarities with CPO because for its policy updates. But the difference between that is that unlike premium dual optimizations, where the dual variables are stateful and learned alongside premium variables, the CPO computes new dual variables from scratch at each updates. And it also differs from the constraint satisfaction is that this approach ensures exact enforcement of constraints, distinguishes CPO from methods where only the policy at convergence is guaranteed to satisfy the constraints. So as we mentioned earlier, so CPO makes sure that at each iteration, the safety policy is satisfied, unlike the other approaches where it's only satisfied at the time of convergence. And it's an innovative approach for CPO because CPO's methods, comparing with the other related works, compute dual variables fresh significantly contribute to its ability to adhere to the safety constraints during the learning process. So knowing the background and the overview of the CPO, now let's dive deep into the algorithm parts. So the objective of the CPO, as we discussed earlier, is trying to optimize the policy performance while ensuring that the safety constraints are satisfied at each iteration. So it has two key features for the algorithm. The first one is to make sure the constraint is satisfied, which employs a novel approach to calculate dual variable anew at each update. And also how the policy was updated. So similar to primary dual methods that we showed earlier, but it was a unique computation of dual variables to enforce safety constraint effectively in a CPU algorithm. So on the right-hand side of the slides, I have attached the algorithm that's been shown in the paper in here, and let me break it down one by one. So in the algorithm that's proposed by the paper, it has several parts. So the first part is initialization, which begins with initial policy within a defined set of policies and a significant tolerance for constraint and satisfaction. And after that, it will jump right into iteration. And for each iteration, it has 7 different parts. The first part is sampling, which collects a set of trajectories based on the current policy parameters. And after that, it estimates from the policy gradients, Hessian or constraint values using the collected data. And after that, it jumps into the dual problem solver. So if the approximate CPO is feasible, it solves a dual problem to obtain optimal Lagrange multipliers for the constraints. And later, it computes a new policy based on the solution to the dual problem. And after that, it tries to, if the approximate CPO is not feasible, it will compute a recovery policy proposed instead, and adjust to the policy parameters later by backtracking a line search to ensure that satisfaction of the sample estimate of the constraints. And after all of that, it will finally update the new policy parameters for the next iteration. So that's the basic idea of the CPU algorithms and how it's being done. And here are some of the results that's shared by the paper and some of the key findings as well. So there are 3 different key findings when we see the results from the CPO in comparing with other different approach. So CPO consistently achieved or exceeds the performance benchmark algorithms while strictly adhering to predefined safety constraints. And also, it showcased an unparalleled ability to maintain safety across all testing environments. And also, it is very efficient because it demonstrates that it can effectively balance the trade-off between exploration and exploitation under the constraints. And on the right-hand side, I also attached the figure 1 that's being presented by the paper in here to give a comparative analysis. So let's give the conclusion first. So as you can see from the paper on the graph, the CPO outperforms traditional reinforced learning method and other safety-aware algorithms in terms of both safety efficiency, and it also highlights the cases where CPO uniquely succeeded in maintaining safety where others failed. So let's dive deep into the figure 1 and see what it shows. So as you can see from the figure 1, it shows an average performance for CPO, PDO, and TRPO over multiple seeds in different environments, which highlights how CPO drive the constraints function almost directly to the limit in all experiments, unlike the other approaches. While PDO frequently suffers from over or under corrections, and also this figure is pivotal for demonstrating how CPO's effectiveness in enforcing constraints while optimizing performance, providing a clear visual comparison how CPO maintains constraint satisfaction across various tasks comparing with other methods. So jumping into the results, there are the key result is it highlights the main achievement CPO, which includes the ability to effectively balance performance optimization with constraint satisfactions. And there are other key highlights, including the safety of that, the performance, as well as the comparative advantage, which we discussed earlier. And it also implies that in the future, how broader implication of CPO success for the field of reinforcement learning, especially for application requires stringent safety measures. And I also attached the figure 3 from the paper on the right-hand side of the slides, which highlights the impact of using cost shaping in the constraints while trying to optimize and generally improving the agent's adherence to the true constraints on C return. So, in conclusion, as we know how the objective of the CPO function, as well as some comparing the result of that with other existing approaches, we can see that CPO represents a significant advancement in safe reinforced learning by integrating constraint satisfaction directly into the policy optimization process. It is also safe with good performance and demonstrate the capability to achieve optimal policy performance while strictly adhering to safety constraints across various tasks. And it also sets a new standard for future developing safe reinforcement learning applications, which promises for future research and practical implementations in a safety critical systems. And thank you. That's the end of my presentation for the paper. And now let's jump into the question part that's being presented by Siyan. So after reading the paper, Siyan asked 3 questions, which I've listed above, and I'll answer each question one by one. So the first question is, what theoretical results underpins effectiveness of CPO? So I think based on the paper, the effectiveness of CPO is underpinned by theoretical results that established a bond relating to the expected returns of two policies to an average divergence between them. So this bond provides a foundation for the policy improvement step in the CPO, which guarantees that both an increase in reward and a satisfaction of constraints on the other cost. This result extends and tightens known bounds for policy researching using trust regions, offering a tighter connection between the theory and practice of policy search for deeper reinforcement learning. So the second question posted by CN is, how does CPO handle high-dimensional control tasks? So I think CPO handles this task by training neural networks policies with thousands of parameters, ensuring both reward maximization and constraint satisfaction. The algorithm employs a trust region approach with surrogate functions that approximate the objective and constraints, allowing efficient policy updates even in a complex environments. So this method avoids the need for off-policy evaluation, which is challenging in high-dimensional settings by using samples collected under the current policy to estimate the surrounding surrogates and guide to optimize the process. And the last question is, what makes CPO distinct from previous approaches to constrain reinforced learning? So I think we showed some of the backgrounds in the presentation comparing with Prim-Dual method, but I will give you a more detailed answer or response here. So CPO, I think, is distinct from previous approach in several different parts. The first part is it's a general purpose algorithm with guarantees. So it is a first general purpose policy, I think, that search algorithm for constrained reinforced learning that offers guarantees for near constraint satisfaction at each iteration. And also CPO is based on novel theoretical results that provides a bound on the expected return difference between policies, facilitating in a principled approach to policy improvement that represent constraints. And third, I think it employs a surrogate functions and a trust region method, making it practical and efficient for high-dimensional control tasks, unlike previous methods that might require off-policy evaluation or lack guarantees for constraint satisfaction during the training. So overall, I think CPO's unique combination of theoretical robustness, practical efficiency, and the ability to handle constraints makes it significantly advancement over the previous constraining reinforcement learning approach. So that's my responses to the 3 questions posted by CDN. And that will be the end of the presentation. Thank you so much for listening and hope you'll have a good day. Thank you.